minute. Hello, everyone. Thank you very much for coming back after the break. Before we get into my topic about recommendation engines using artificial intelligence, can I just give you a small riddle so that we can raise our minds for a minute and then come back to the AI topic? Okay, are you guys ready?
Yes.
Yes? Okay. A little girl goes to a store, wants to buy a pencil. She has a $20 bill. I come from the United States, so I'll just use dollar bills. And the pencil costs $5. And the storekeeper gives her the pencil, but realizes he didn't have change, so he didn't have three fives. So he goes to the next store and gets a change for the $20, gives $15 off to the girl, along with the pencil, and off she goes. A few minutes later, shopkeeper 2 comes back to shopkeeper 1 saying that this $20 bill is fake. Can I get my 20? So shopkeeper 1 says, oops, sorry, and he gives him a different $20 bill. In the whole process, how much did shopkeeper 1 lose? That's a question. So if you have an answer right away, go ahead and think about it, let me know. Otherwise, I'm going to go through my presentation, and towards the end of my presentation, I'll tell you the answer.
$5.
$25, $5? Okay, cool. Yeah, keep that in mind. If you have any other answers, meanwhile, we will talk about that. Recommendation engines have been there historically for a long, long time. But the accuracy, the prediction capabilities, and the way you can process large amount of data has gone up tremendously in the last 4 or 5 years. I would say even a search, basic search you do on Google is a type of recommendation engine. You actually can get hundreds of thousands of responses to a single search, but the Google search engine or any other search engine has to intelligently arrange what would be the most interesting for you as a person, what you're looking for. Now, here it becomes complicated in terms of what you're looking for may not be completely reflected in the search keywords you've given. Or even if you're looking for a movie or a book or the point of interest, let's say you're going on a vacation, you want to find the right vacation spot, there's a lot of other information which you're not providing to the recommendation engine, but if you are developing a REX's model, recommendation systems model, then you got to understand how this works. And I'm actually going to talk about how recommendation engines can be developed. Even though I've done a couple of recommendation engines in my life, I would not be revealing the guts of that model. So in the process, I can explain some of the published works which have inspired us. And I've picked a few most popular models available in the world, and then we can talk about that. Before I get into the actual details in my slides, can I give a quick round of how many of you believe you are real techies, or how many of you believe you are more of a managerial, we are managing people, but know a little bit of tech, but we would prefer to be called as managers, because then I can customize the presentation, whether to get into the details of techs or not too much into the details of the tech. How many are managers, pure managers? Okay, fantastic. How many believe you are tech, you can understand tech? Okay, cool. So it's a balanced thing. So I'm going to talk both. And this is the scenario where I think it's going to be difficult for me, because if you have half of them are tech and half of managers, I'm going to actually see how much I can do the balance. I know I have another 25 minutes, I think, to go. People have done, companies like Google, companies like Facebook and Amazon have done millions of person effort to design a recommendation system. I'll talk about that, how they've done in the next 25 minutes and see. First, a few fundamentals. Recommendation engines used to be historically developed based on the explicit feedback the people have given to the model. For example, you buy a book and you say, oh, I like the book. Or let's say you watch a movie, or so you say, oh, I like the movie, and I give a rating of 3 stars, or on a scale of 1 to 10, maybe a certain number. So that's a feedback the model constantly gets, which is what companies collect data so that they can make a recommendation engine which is more and more accurate and nice. That's called explicit information. But sometimes, or rather many times, there is not much of such information available. And then companies resort to implicit information. For example, you may not have given your feedback on a video you've seen, but the fact that you have seen the entire video, that is, if it's a 30 minutes video, you've seen all the 30 minutes, or a movie, 2-hour movie, you saw the movie for 2 hours, there's a high probability that you actually like the video. even though you have not said that in so many words. And that's called implicit feedback. So explicit and implicit are two different factors. Many recommendation engines which have been developed for the last 2 or 3 years actually are based on the implicit information, because sometimes you may not have given the accurate information even if you have given the feedback. So many companies don't mind ignoring your explicit feedback and focus on the implicit one. And there are two fundamental approaches, again, some more fundamental details, two fundamental approaches being used in developing recommendation engines. It's called content-based filtering and collaborative filtering. Let's say you bought a book called Outliers, and another person bought a book, Outliers plus Predictably Irrational, that's another book. And if the model feels that you and this person are very similar in their tastes, that's called the latent information about these two users, then the model would believe that you might also be interested in the same book what the other person bought because you both are similar. And it was purely based on that's called collaborative filtering, because you're trying to watch what these two people have done. Content-based are, if you buy a book, let's say Outliers, and you bought another book which is in a similar theme, let's say a self-help kind of book, then all other self-help books may be interesting for you, and the model starts recommending those things. So those are the two fundamental topics. One more fundamental detail again. When you get the details, when you get the feedback, the users give feedback on an item, you actually put it in a matrix. It's called a user item matrix. And many times this matrix is a very sparse matrix. You have this matrix I mentioned here. You have the users mentioned on the column, on the items mentioned on the horizontal. You have whoever the users and items could be your books or movies or videos you want to watch. And there is some mathematical equations you can use. For those who are techies, who I can explain, when you get explicit feedback, the way you train the model is you are actually designing a loss function, and you use the loss function to train the model how it is. If RUI is the matrix of information you got based on the users and the items, and that compared to two other matrices, which one for your user, one for items, and you do a mathematical computation to design the loss, and you can train the model. And this is a very basic equation. You can also add some global and local biases to the model to avoid, let's say you already bought an online app for, let's say, fitness. The probability of you buying another fitness app on your mobile device is quite low. And if you have seen a movie which is an action-based movie, the probability of you seeing the action-based movie is higher. So, and hence, you've got to be careful about those local and global biases, and hence you can take care of that. And similar mathematical equation for implicit feedback also can be computed. There are lots of techniques available, how you can use recommendation engines, but I'm actually going to skip this. The most famous app I think all of us have been using is YouTube. For that matter, let's do a quick role play. Imagine 15 years ago, 20 years ago, if you were to be the investors with lots and lots of money to invest in a startup company, and if I were to be a startup a guy, and I'm pitching my idea to you and say, you know what, I'm developing a new company which is going to let users upload whatever videos they have. I'm going to design user tools which is going to make it easy for these users to upload their video. I'm not going to charge a single penny, but by the way, I need millions of dollars to have this huge infrastructure for this company. And I don't have a clue how I'm going to make money because I'm not thinking of any ads for that. Would you have invested in that company? Yeah. Now I think post-facto we all like. That's YouTube I'm talking about. The company, I think when they started by two American young guys, I think one is a Vietnamese or a Chinese immigrant and a couple of other guys too. There are billions of, at least more than 1 billion users accessing YouTube. And I was told thousands of hours of content is being uploaded every minute into YouTube system. When you give a search for what you're looking for, the recommendation engine in this case, what they've done is they actually have two neural network models. One would first do a candidate generation. Out of the hundreds of thousands or even billions of YouTube videos. They want to pick a few, maybe a top 100 or top 1,000 that may be relevant for you in this context as a user, and then rank maybe the top 10 or 20 or 50 that will be useful for you. Candidate generation is a more cruder neural network. I think you can see it here. A variety of user factors, including the search factor, the search keywords, certain geography information, including demography information of the user, would be combined into some sort of an user embedding. And if you don't know user embedding, I think we can talk offline. But you have the embeddings of the videos you watch. These are typically the words which describe the videos, and also you have information about the user, like the age and the gender, and also you have the geography, and also the search tokens, what the user is giving. All of these user embeddings are combined into a search, and the model actually does a little bit of a neural network, and while training, it does a softmax to identify the classes of videos that need to be retrieved. This is typically a crude method. It returns in a few milliseconds. I think 20 to 30 milliseconds is the target YouTube has to retrieve the candidates. But the more important is the ranking part of it. How do you rank it? And they use similar embeddings, but the structure being all the same. The model generates the candidate, I think first 20 milliseconds, and I think another 20, 30 milliseconds, I think it does the ranking part of it. The complication in this whole process for YouTube video recommendation is, even though you have watched an action movie, or let's say you saw a song by Taylor Swift, the probability of you repeating the same action movies or watching the songs of Taylor Swift, I think, is quite lesser. So the model actually, instead of taking a sequential approach of what you've done in the last few minutes or few hours or few days, it does a concept called bag of words. It actually jumbles up all your browsing history in such a way that you would see more of what you were looking for in the recent past, but you would still see what you liked or what you searched for maybe a day ago or a week ago or even older. The number of such videos will be lesser and lesser, but the model actually combines all of these things. That's a unique part of YouTube, because they figured out when you start looking for something, you just won't show all you Taylor Swift videos alone. It has to show other things too. Another complication if you're developing a recommendation engine is, many times in classical machine learning methods where you can use accuracies and precisions and F1 factors as metrics, or if it's an NLP-based model, you can have blue scores or rogue scores. These are a bunch of metrics available. But in a recommendation engine, you would not know whether you're doing a good job or not unless the actual users who are trying to use it give a feedback to you. So the most number of instances when a recommendation engine is developed, the companies actually have to do an A/B testing to find out the feedback, and that's what. And in this case, when YouTube developed this, they found a very high accuracy rates. This was a paper published. By the way, I'll be showing the papers at the bottom of every slide, or all the information I'm going to be sharing is published, and it's at the bottom of the slide. This is a second paper they published, I think, in 2015, but I think the first paper was in 2013, which was not as efficient, but this is an improvised version of it. That's about YouTube. So it comes with certain way of people looking for videos. Now, a different recommendation engine is identifying what's the right app. Let's say you're searching for app to download on your mobile device, then the logic, even though seems to be very similar, but I think it has certain fundamental factors which are different. This is a Google Play recommendation model, which was published as recent as a year and a half or 2 years ago. When you want to, let's say, if you had a fitness app, you wouldn't go for another fitness app on the same mobile device, but there may be an app which actually goes with it. Let's say maybe a music app, because now that you have a fitness app and hopefully you're going for a run or doing exercise, you may go for a music app or information about a health app. That's what is required. When recommendation engines are being developed, I've talked about the sparse data, but many times when you use the data, what the users have given both explicitly or implicitly, you would only have this model which is intelligent based on the existing data. Let me give an example. If there is a new song or a new video that comes in, if the model is not trained on taking care of those information that's coming in latest, but only rely on the past data, then newer information that's coming in is never picked up. In the case of YouTube videos or in the case of new apps, one is it cannot be the same app you make a recommendation to. Second is you have to constantly look for newer apps. So in this case, if you look into Google Play, what they've done is they mixed two different approaches. One is called the memorization technique, and the other technique is called generalization technique. Memorization is if there are 10 users and 10 different types of apps they are downloaded, you constantly understand what these people are doing, and a new person comes in, you actually make a recommendation based on the past history. That's a very linear way of recommending. That's one of the best ways because it is scalable, extremely scalable, and can easily understand what's happening. The dynamics between the users and the interface in items is easy to catch. But the problem with that is any newer apps that's coming in, because the model has never seen that in the linear model or in the memorization model, because you're memorizing the information and processing it, you've got to have a different way of doing it. And in this paper, they published two, both wide and deep model. Deep model is a neural network which actually processes lots of information about the users, the apps, and their browsing history and the download history and their feedback all together to understand what may be the right app they should recommend for the next one. But also they do a cross product, which is actually a wide model where they using the memorization. So this technique would go for the memorization, just this part, and then this would be the generalization model. Google actually did a fantastic job, and then they got a very high accuracies on this. I was told it's 10 more minutes. I'm going to have at least 5 minutes for question and answers, and I'll talk about this recommendation engine. You have the videos, you have the apps. Text recommendation, that is a news recommendation, is driven by entirely different dynamics. News becomes stale very, very fast. Within 24 hours, you just don't like any more information about yesterday, but you want the latest information. That's number one. Number two, let's say there's an event that's happening that's called evolving event. There's an event happening right now, let's say a terrorist activity or floods or maybe the football games going on. The news that's being published, let's say in the morning of today and the evening of today and the morning of tomorrow, even though it's almost the same topic, but there's some more information that's coming in. So the model has to understand not just the overall theme of the news, but also find out how similar and dissimilar the model is. So this is a solution proposed by Yahoo News for Japanese customers, and if you look into it, this is a typical view on your mobile device, but what they do is they use two different aspects. One is the user browsing history. Every time you go and give a search, it actually gives you a few recommendations. So this is a browsing history, and at any time point t, you get a bunch of recommendations, and based on what you have picked, it goes to the next time zone, t+1, and then the model is understanding what you're proposing and what you're recommending. Here, what if the model finds 10 different articles which are relevant to you, but all happen to be on the same topic and all happen to be on the same news item, which doesn't make sense. So there has to be a different method of identifying if it's called cosine similarity. If you convert a text, a bunch of words into certain vectors, they can use a lot of techniques for the doc to vec or word to vec, or even I think document paragraph to vec. You can find out the cosine similarity, which means how similar these two articles are. The closer the article is, the higher probability you discard that, because the first one and second one, if they're close to each other, that means they're both same, so don't show them, and that's another way. So you track the browsing history with the information about what the user is watching or searching, and also find out which of these articles are similar and dissimilar, and then do this little bit of a ranking process that happens and then gets picked up. I'm actually going to show one last. This is a very, very exciting topic. I think it's published in 2017. When data that comes in by the users, about the users and about the items, many times the data may not be accurate. People have to be aware of the fact that the data is inaccurate. a concept in neural networks called autoencoders, which came up, I think, really got popular a few years ago, 4 or 5 years ago. Autoencoders is a type of a neural network which takes a bunch of data, produces the same data by doing lots of processing, but this time the input data, which may be slightly erroneous, when it creates the output data, is slightly better in quality data. Now, there was another technique that came later on called autoencoders, where instead of giving the incomplete or slightly erroneous data, you actually add more errors into the input data and train the model to create the right data. So autoencoders take slightly erroneous data, artificially erroneous data, and then create a good data. Now, that concept was used to create 2 different encoders, and here it's called additional autoencoders, denoising encoders, which will not only take away the error from the input data, but also takes additional information. So there was one neural network or one autoencoder network which is giving the user type of information which was artificially made erroneous, but also insert the user related information. And similarly, another autoencoder which takes the item information and also gives the latent information about the items, and combine these two in a matrix factorization method to make a recommendation. This was a spectacular addition. I'm guessing in the next 6 months to 1 year, newer recommendation engines that's coming in would have a lot more of this technique of using autoencoders in their models. Okay, let's see. Point of interest is tourism. People are using in tourism, and if you go on a vacation, the model is recommending what would be the next point of interest for you based on so many information. And there's another successful model that's available. That's from my side. If you have any questions, I'll be happy to answer.
To what extent are people using implicit feedback when they're doing A/B testing instead of just on the live systems?
The implicit data is being used to train the model. Once the model is trained, the model starts making recommendations. That recommendations which is being used will be used for A/B testing. And that information, what you get back, would be fed back into the system. But there are 2 different areas where you're using the information. Implicit information is used for training the model, and A/B testing is done when the model is trained and now it's being tested. So instead of just testing the existing data, they do that, but at the same time they use it with A/B testing, because the real way of finding whether you've done a good job in developing a good model is give it to the people, and people will tell you whether they really liked it or not. So that's an A/B testing.
How are they telling them how they really like it? Is it only through the explicit feedback?
Yes. Not necessarily. Like, for example, if you make a recommendation of 10 videos and they pick one of your videos instead of picking some other video of what you didn't search, maybe they have a URL, they're going to go for that video. That means your top 10, what you thought were top 10, did not go fine. So then you get the feedback saying that that's an A/B testing. You say, okay, my recommendation is not working fine. So they'll go back and say, what video did this user pick? And what seems to be the latent factors of this video that is different from these 10 videos I proposed to him or her? And then you start going back and looking at the data. Yeah. It's almost nowadays it's all implicit data. Hardly people use explicit data, because people don't even give feedback nowadays explicitly. Yes, sir.
What metrics? I'd like to know what metrics you use to optimize a recommendation.
The results of A/B testing is the only metric people are using nowadays to optimize it. The moment you make a recommendation and the user is not picked, even though there could be so many reasons why the users did not pick, but they would go with, if you picked it, that's fine. If you don't pick it, they'll look for what you picked and then go back and see the latent factors of these 10 recommendations versus this, and then put that data back into the system to see if you can understand what's happening. Many times, depending upon how dynamic your recommendation system is, you wouldn't do the retraining part of it every day, maybe every 3 months, maybe every 6 months you do a retraining. Let's say if it's Netflix, maybe they do it every month, maybe 2 months, because of the content that's coming in. Apps, maybe I think every quarter or even a little slower.
Are companies feeding data into recommendation systems that exist outside of their own organisation? So I don't think Netflix would necessarily get this, but Netflix will get what a user looks at within the Netflix environment. they also try to feed into figure out information such as browsing history or looking at any other information outside of their environment they can collect to base a recommendation system on.
Yeah. Netflix, I don't know.
It was in general.
I know, got it, yeah. Yeah, so if companies do not want to use the data coming from a third-party source because you are not exactly sure that information really is useful for them, even though it may be on the same, maybe they're doing a similar business model, but they don't want to do that. They want to actually use their own data system that's coming in. So let's say if it's Amazon or Netflix or whatever companies, they want to use their own data. But companies, let's say you start a company today and you start selling your books, let's say, and if you don't have any information about your customers, that's called cold start. There are multiple ways of doing a cold start. Let's say if you don't have any data, then you actually take a third-party data. In that case, you're actually taking a little bit of a gamble to say, okay, fine, maybe I'll start using it. And you start building your own data. But all the existing companies with existing models, they would just rely on their information itself. Any company, I think they just I did have a paper which I did not show today. It's called from Zolanda, which is a fashion recommendation model. They do have a fantastic implementation of a recommendation. Let's say you buy if you go to the store, if you go to the online store, if you go to a physical store, or if you bought a little bit of things, the moment you walk in, they would know who you are, what type of dresses you like. Especially, I think the females, I think they have more information, and they would start making recommendations. Okay, thank you very much.